Hello, I'm Joe Bakhos. I am a high school physics teacher. In this video, I would like to share with you what led me to propose a solution to the dark matter and dark energy problems in astrophysics. And so the first thing to ask is, what is the problem? Why did physicists propose these two ideas, dark matter and dark energy? Why was it necessary to propose these things? And what is current theory, basically? So let us start with dark energy. Scientists proposed dark energy because, for some reason, the galaxies in our universe seem to be accelerating away from each other. Now, if you have an explosion or something, and we can kind of think of the Big Bang as if it is an explosion, it would be normal for the objects to, out in space, since there's no air resistance or anything, we would expect them to go at the same speed away from each other forever and ever, traveling at the same speed away from each other. And maybe after a great deal of time, they might slow down because of gravity and start coming back together. But when scientists looked out in the universe, that is not what they found happening. Instead of the galaxies moving away from each other at a steady speed, like you would expect after an explosion, instead the galaxies are accelerating away from each other. And that is strange, because whenever you have an acceleration, that means you must have some kind of a force. And so, because the galaxies are accelerating away from each other, that is not like a regular explosion, and we have to posit that there's some sort of force pushing the galaxies apart, and we call that force dark energy. And so this force we're positing to explain why the galaxies are accelerating away from each other, why do we call it dark? The reason why scientists call it dark is because we can't seem to detect it in any way, and we can never replicate it here on Earth. The other four fundamental forces that we have, we've got the strong force, we've got gravity, we've got electromagnetic, we've got the weak force. All those forces, we can observe them operating here on Earth. But whatever is causing these galaxies to accelerate away from each other, we don't know what that force is. We can't replicate it. We can't detect it. So it's this great big mystery. And so we call that dark energy. So that is dark energy. The reason why scientists posited dark energy is because galaxies are accelerating away from each other and we don't know why. So that's dark energy. So what about dark matter? What caused scientists to come up with an explanation involving dark matter? That has to do with the way that stars go around the center of a galaxy. We have ways of finding out how massive a galaxy is, and with that knowledge, we know at what speed stars orbiting the galaxy should be orbiting at. And the problem is, the stars are going too fast. With that given mass, and at that given distance, those stars at the speed that they're traveling at, they should be flying off into space. And instead we see that they are held firmly in orbit around the galactic center. Okay, so if this is a typical galaxy, what we're seeing is these stars in the outer edges of the galaxy, they are moving too fast and they should be flying off into space. In other words, the mass that we are seeing is not enough mass to be holding them in place at that speed. So this means one of two things. Either there's more mass there, mass that we cannot at all detect, or else gravity is stronger at these distances than our current theory allows it to be. So which is it? So we have this mass in most galaxies, so let's say our galaxy, and this mass, we call it dark because we can't detect it. But let's be careful to say what this dark matter is not. It is not simply like dark dust or gas that we can't see because it's dark. If there was dust or gas there, we would be able to detect it because light would be refracted by ordinary matter. So this matter is of a type that is not ordinary. It's of a type that cannot be detected. It doesn't interact with light at all. So it's not matter as we know it. And so once again, because we have no way of detecting it other than these gravitational effects that we're observing, we call this dark, dark again. So we call it dark matter because we can't figure out what it is and we cannot detect it. Thus, dark matter and dark energy are posited in order to explain galactic rotation rates and also cosmological expansion. But there's a downside. The downside is we can't seem to detect them anywhere close to home. Any experiments we can do on Earth, we don't see these forces. We don't see cosmological expansion. We don't see evidence of dark matter, nothing that we can detect. So I am proposing modifying our gravity theory instead. But if we modify gravity according to what I'm saying, which is that gravity varies as a dampened wave function. And so sometimes gravity is positive, what I'm calling positive, meaning attractive in the way that we're used to. And sometimes gravity is negative or repulsive. Sometimes gravity is more than what we're expecting. But when we look at the celestial objects in our solar system, they all seem to follow very precisely gravity according to current theory. And so I would like to share why I think that is, and I would like to present some evidence of certain objects in our solar system that have shown that they don't operate under current theory of gravity. So I would like to look at 4 different topics of items within our solar system that might back up what I'm saying, a modified gravity theory. One of them is the Pioneer Anomaly. One of them is the Flyby Anomaly. One of them is Oumuamua, which is an interstellar asteroid that recently passed through our solar system. And the last topic is comets, the way that they show anomalous accelerations. If you would like to know a little bit more in depth on each of these, please feel free to Google them. They're all well-known phenomena. Let's first start with the Pioneer Anomaly. So when the space probe Pioneer was launched, once it got out, I believe, out past the planet Jupiter's orbit, and perhaps before, it depends on the data, it experienced some unexplained acceleration, and the way the acceleration manifested was as if something was pushing it away from the sun. Now I've drawn these orbits. The black lines represent the orbits of the planets. You can hardly see the inner planets. Mercury, Venus, Earth, Mars, they're all in this inner planetary circle. And I'm sort of putting, with a highlighter pen, areas that, according to my idea, might be repulsive gravity. Like a probe that passes through those areas would feel a repulsion from the sun rather than an attraction. And so I think that this would explain the unusual acceleration that Pioneer experienced. Now, for quite some time, scientists were trying to figure out what had happened, and the reasonable, rational explanation that they've come up with is that Pioneer leaked fluid or leaked gas, and that this was the cause of the anomalous acceleration. While I feel this is reasonable and it is possible, I think that it is mistaken. The second item I'd like to talk about is the Flyby Anomaly. We sometimes send probes near a planet to get a slingshot effect to help the probe accelerate further or else decelerate sometimes. And they find that when they do this, they're getting more of a boost than what they were expecting according to current gravity theory. And at this point in time, this cannot be explained. This is another item of evidence that I feel shows that gravity does not behave according to current theory. The third item I'd like to talk about is Oumuamua. Oumuamua is an interstellar asteroid. It was discovered by an observatory in Hawaii, and they named it Oumuamua. And we can see here this white path coming into our solar system from above the solar system plane. And Oumuamua also showed an unusual acceleration. At one point, it was feeling some kind of force pushing it away from the sun. And I think this is also evidence that gravity does not perform according to current theory. Oumuamua caused a huge debate among scientists because it did not have a tail like a comet. Comets also have anomalous acceleration, but scientists have always explained that because of off-gassing. That as comets get closer to the sun, they emit this gas, and that's what presents the tail of a comet. And this gas also causes anomalous acceleration, according to current theory. And so some scientists were saying maybe Oumuamua was off-gassing. Now, I think this is mistaken in both respects. I think that current theory is mistaken about comets. I think that the reason why comets will have anomalous accelerations is not because of off-gassing. I think it's because they are in a very eccentric elliptical orbit. I believe that comets have anomalous accelerations, not because of off-gassing, but if you look at their orbit, it's like very eccentrically elliptical. So a comet's orbit might look something like this, you know, going way out like that, coming in close to the sun. And the reason why, in my opinion, comets have anomalous acceleration is because of their elliptical orbit. They pass through regions of repulsive gravity and regions of attractive gravity, and this is what gives them the appearance of having anomalous accelerations. I believe that over the course of billions of years, planetary objects or solar system objects are forced over time to come to an orbit that is more or less circular, at least somewhat circular. And when objects are in circular orbit, then they will show only acceleration that is due to gravity in such a way that is consistent with current theory. Let's go a little bit more into depth. In the website that is coming up now, I've put a link where you can download a PDF file of this article, or you can read it online at this site if you prefer. I have come up with a trial wave function, which I'm sharing here, just using data fitting. And here I'm just assuming that gravity varies with mass and distance as a dampened wave. So I propose this equation, and it's just a first guess. It's a starting point. Here is the equation. Here A stands for acceleration. G is the gravitational constant using meters, seconds, and kilograms as units. And R is the distance from the sun. If the images are blurry, as I said, you could go to the website for a clearer look at it. In this diagram, these purple dots here represent the planets, Mercury, all the way through to Jupiter, including the asteroid belt here. And in this diagram, the red line represents the strength of acceleration due to gravity according to the trial wave equation. That's this red line, and you can see as it's moving up and down as a wave. And the blue line represents the acceleration due to gravity based upon current gravitational theory. So that is the blue line here, and you can see how all the planets are exactly on the blue line according to current gravitational theory. So anywhere that the red line goes below the x-axis, like down here, in these regions, gravity would actually be repulsive. It would be pushing rather than pulling. One thing to keep in mind is that thus far, this is only a guess. As I said, it's just using data fitting, it's just a first approximate guess. When we look at actual data, the wave function that we might come up with to fit the data may be quite different. I mean, even it might be flipped where these peaks are down here. The whole thing might be flipped across the horizontal axis, and things might be spread out a little different. So as I said, this is just a first guess. The point that I'm trying to make is that gravity varies as a wave function from a positive peak to a negative peak, and it just goes on and on like that forever. So if gravity does vary like this, there's a good question. Why has no one noticed this before? In the 1800s, Joseph Bertrand proved that only orbits subject to a force that's proportional to r squared would be stable. So matter would only be settled into these bands, or else it would be in an eccentric elliptical orbit lining up with Bertrand's result. When we look at the graph that compares the wave equation with the standard equation, this means that orbiting bodies eventually, over billions of years, would settle into places where the red line intersects the blue line, and that is roughly where we see the planets. As I said, this is a rough approximation right now, but I'm thinking that once we refine things a bit, these points will intersect much more clearly and more regularly. That's roughly where we see the planets. It's interesting to note that this also might be why Saturn's rings have gaps between them. The gaps may be places where gravity is repulsive. It might be that when Newton first expressed an equation for the gravitational force, what he was really describing was Bertrand's theorem. So what I mean to say is that in these areas here that I've kind of highlighted in yellow, these areas in between the planets, they may actually be regions where gravity is repulsive. So over the course of billions of years, all matter would have been repulsed out of those areas. Since there wouldn't be anything in these regions to observe, scientists may have been misled into thinking that gravity is only attractive. There's a second reason why these effects might not have been noticed, and that just has to do with how strong the gravitational force is at these distances. It's not actually that strong. To give an example, at planetary distances, let's say the Earth's orbit, the gravitational force causes an acceleration to the sun of about 0.052 meters per second squared, so 0.052. Well, the Earth is traveling at something like 30,000 meters per second around the sun, and our probes travel at similar speeds. And so when these probes are traveling that fast at speeds, 15,000 or 30,000 meters per second, a slight variance in acceleration, like 0.052 or meters per second squared, or something similar to that, might not be noticed. Or else, if it was noticed, it would be attributed to the gravitational effects of Jupiter. It might be attributed to leaks of gas or liquid that escaped from the spacecraft. It could be attributed to various things like that, because the variation at these distances would actually be quite small. But these things are not actually the biggest objection to this hypothesis. The biggest objection is that we already have a gravity theory, general relativity, which we sometimes abbreviate GR. And this gravitational theory works extremely well. It has been tested over and over again. And all the tests so far show that it's valid. And so we need to delve into that a little deeper in this next section. How do we deal with the objection that GR seems to be completely adequate at this point? Einstein posited general relativity to deal with some interesting commonalities between two things that we would not normally think would be related. So objects that are at relative speeds approaching the speed of light, and objects that are coming into an area that's greater and greater and greater gravity, like say an object that's approaching the sun is experiencing greater and greater gravity. So what is it that these two types of objects experience? I mean, what's the commonality that Einstein was dealing with? In both cases, the object gains mass, and also for that object slows down. So as an object approaches the speed of light, or as an object descends into a strong gravity well, it gains mass. Well, strictly speaking, in a gravity well, it gains weight. But in this context, I'm going to use the words weight and mass sort of interchangeably, even though that's not quite correct. But in any case, so in both cases, the object gains in mass, and time for that object slows down. So Einstein deals with these two kind of odd commonalities with his general relativity, as we said, abbreviated sometimes GR. So in GR, Einstein treats time as if it's sort of like a fourth spatial dimension. And so time and space have four dimensions. And in this construction, both time and space are subject to warping. They can expand, they can compress, they can curve. For instance, space, Einstein supposes curves near sources of strong gravity. And for objects traveling near the speed of light, space is compressed. I would like to give a different explanation for these commonalities. First, I would like to explain what time is and why it's not quite correct to think of it as warping or compressing. And I say that because I believe it's not a dimension like that. It should not be attached to space as if it's a sort of fourth dimension. And so first I would like to discuss what I think time is. Time is the record of change. If there is no change, there is no time. So for example, if every molecule, atom, subatomic particle were suddenly frozen in place for 1 million years, and then after that period of time we're suddenly allowed to proceed normally, there'd be no way for us to tell that any time had passed. Because the only way we can tell time has passed, in fact, what I think time is just change. If there is no change, there isn't any time. So in that sense, any point in time, what we mean by that is simply the current arrangement of every item in the universe. That is a point in time. And so if someone were to talk about going backwards in time, all that would mean is returning every single item in the universe back to the position it was at that time. And so in this sense, time is not a dimension that you can travel through. So it should not be thought of as a fourth dimension of space, because that's not what it is. Time is simply the current arrangement the current position that everything is in. So why does time slow down in a gravity well? If we get super powerful gravity, why do we notice time slowing? I believe this occurs because as the lines of force, and I believe everything is subject to gravity, as the lines of the force of gravity, as that force becomes stronger and stronger, any molecule or atom or subatomic particle has more and more of a difficult time rotating out of the line of that force. And so every atom, every molecule, every subatomic particle has a harder time moving because it can't rotate out of that axis. The lines of force are so strong that it can't wiggle or move the way that it normally does. And so because that cuts down on the actual change of all the constituents of that mass, whatever it is, because change is cut down, time is cut down. So that is why time slows in a gravity well. The same thing happens as objects approach relative speeds near the speed of light. And so I am going to draw a connection between these two things, the way objects behave near the speed of light and the way objects behave in a gravity well. I'm going to draw a connection between these two things that is different than the connection between them described by GR. So I'm going to posit that mass and relative speed are related in a way that's similar to the way electric charge and the magnetic force are related. In other words, I'm going to claim that relative speed produces gravity, and gravity also produces relative speed. So they're in kind of a mutual relationship, as I said, similar to the way that the electric force and the magnetic force are related. So as an object approaches the speed of light, its mass heads towards infinity, and the gravity expressed by this mass also heads towards infinity. And this gravity causes the same slowdown in time that objects experience when they're descending into a strong gravity well. This also then might explain why gravity varies as a dampened wave function. For any massive object like the Earth, for example, there'd be a huge quantity of relative motion going on. If you just think of all of the molecules, atoms, subatomic particles, all tied up with the Earth, all moving constantly, vibrating back and forth, this relative motion, according to what I'm saying, may be what generates gravity. So I'm therefore saying that maybe GR can be adjusted such that we keep the idea of increasing mass, and we also keep the idea of time slowing down, but maybe these things can be related in such a way that we no longer keep the idea of warped or curved space, because I don't think that is necessary to the construction. If this is all true, then it might be some sort of harmonic vibration among all these various motions on something like the Earth or like the Sun. There might be some kind of harmonic vibration among all these things that causes gravity to behave like this dampened wave function so that it is attractive sometimes and repulsive at other times. But all of this is really very speculative. At present, there's no scientific proof at all for anything I'm saying. So I would just like to make a very clear distinction here. All of this that I just finished saying about GR, that is just completely speculative. And so it awaits evidence. But one aspect of the stuff that I've been saying in this presentation, an aspect of this hypothesis, is very scientific in the sense that it is testable. I'm saying that we can look at the behavior of our probes. We can look at the behavior of comets. We can look at the behavior of asteroids like Oumuamua and see if closer inspection shows us that in some areas gravity is actually repulsive. So as I've explained earlier in the presentation, this may have been missed in the past because the amount that acceleration would change at these huge speeds would be very minor and people might mistakenly attribute it to something else. Now it would be different, however, if scientists would look at it in the context of what I'm saying. If what I'm saying is true, they will be able to either demonstrate that it is true, or else they will be able to falsify what I'm saying. And so in that sense, the hypothesis I'm presenting is very scientific, whereas the speculations that I just made about GR are at this point in time just simply speculation. I'd like to conclude here just by running through very quickly all of the things that this hypothesis would explain if it is true. First, I'd like to take a look at these diagrams again. This one shows the velocity of various suns and also other things around the outer edge of a galaxy. And so on the y-axis here, on the vertical axis, is the velocity. And on the horizontal axis is distance from the galactic center. Now we would expect, as an object gets further and further from the galactic center, we would expect its velocity to decrease. And instead what we see is this. And what I'm claiming is, because gravity varies as a wave function, what we're seeing here would be, for example, on this diagram, if we were at like the top portion of this wave. And then, according to what I'm claiming, later on this would come down, okay? And at some point, gravity would turn negative. And then, like for instance, down in this region here, by analogy, for a galaxy, that's when we would have cosmological expansion kick in. And that would be why the galaxies are pushing away from each other. Another thing this hypothesis would explain would be the stuff we find out from the cosmic microwave background radiation, abbreviated CMB. Scientists, when they look at this, it gives us kind of a picture into the early universe. And what they see when they look into the early universe is that matter was very evenly dispersed. It was not in clumps that it now is, that later formed the galaxies and so forth. And according to current gravitational theory, all of this matter has not had time yet to separate like it has. It has not had time yet to separate and become the galaxies that we see today. And so dark matter is posited to have existed back then, already kind of separated into different clumps, and that the gravity from this dark matter sort of pulled all the visible matter, all the normal matter into these regions. And so the relatively rapid separation of matter is explained by that. However, if gravity varies as a wave function in the manner that I'm describing, it could be that a model might be found where, because you have amongst all this matter both pulling and pushing going on at the same time, all of these interactions may have allowed for matter to separate much quicker than current theory allows. Another thing that would be explained is the formation of ring galaxies. This is a picture of a ring galaxy where all of the star systems seem to be orbiting in a ring around the galactic center. And according to the hypothesis that I'm explaining, it could be similar to the way a solar system is formed, where matter ends up in various bands at set distances from the sun. This might also be the case. Eventually, each galaxy might end up looking like this, where all of the suns are arranged in concentric rings or else one single ring. Okay. Some other things that would be explained by this hypothesis would be the behavior of Oumuamua, as I discussed earlier in the presentation, the Pioneer Anomaly, the Flyby Anomalies, and the behaviors of our comets in our solar system. Given all these things that the hypothesis might explain, I hope that I've convinced you that it's at least worth looking into. Thank you very much for watching this video. And if you would like to contact me, you can contact me at the email that is being shown now.